early, like now. Okay, I mean, when I say early, not in terms of good morning, early as being a young engineer. Okay, because I met a lot of engineers, they still have different difficulty differentiating what is a torque and what is a moment. And I'm going to teach you a real simple way to identify. Okay, so I'm going to still do the same thing. I'm going to take this image. Yeah, I'm just going to show you guys this image. Okay. So why is 2,300 foot-pound here a torque and not a moment? And why the 1,500 here is a moment, not a torque? Okay. So if we look at, yes, May, you're absolutely right, depends on the centroid. Okay, it depends. Sorry, it not depends on the centroid. It depends on the position of the neutral axis. Let me elaborate. Okay, so if we look at the formula, okay, we look at the formula. Torque is equal to force times radius. Right? So if you look at, if I'm going to draw this out, right? The dot that I've just drawn, this is known as the neutral axis. No, yeah, sorry. Maybe May is right. Call it centroid. Yeah, May is right. Let's call it centroid. Okay, so this is our centroid. Okay. Then if we have a force, and this will be our radius. And this is also 90 degrees. Okay, so that's how we calculate torque. When we calculate moment, is equal to force multiplied by perpendicular distance. So this is your structure now. Okay. And I'm going to draw, let me draw the same size. And then let me highlight the centroid. Let me do the centroid in green. So now this is the centroid. Right? And then we have the force. Okay, that is our force. And if this is our element, okay, this will be the perpendicular distance. Now, the difference is this. Okay, if you look at the deformation pattern, and the deformation pattern, I'm going to draw in red. Or in orange. Okay, and then I'm going to label this as our centroid. Okay, on the left hand side, where is the torque? Okay, where's the torque? What you see over here is when the force is applied, right? The green dot is still at the same position. Yes or no? Right? It's still at the same position. Okay, good. So during loading, the centroid will be at the same position. Okay, When it is bending, the centroid will not be at the same position. The centroid will deform in this manner now. Okay. So by looking at the centroid, how it's deformed during loading can tell you whether is it a moment or is it a torque. Okay. I've thought of a lot of ways to identify it, to explain to engineers, or being an expert witness, explain to the judge, okay, who has high school physics only. When the last time the judge took a high school physics was probably 40 years ago. This is the easiest way, okay, to identify when it's a torque, when it's a moment. Okay. Anyone, any question, please? Anyone?
Yeah, so pretty much like torque is for torque, like the centroid remains in the same position, but
Yeah.
for a moment it's going to change.
Yes, it's going to have a sad face look or smiling face look. Okay.
Thank you.
Okay, so this is the way that you should identify. Do not memorize any of this. Okay, as mechanical engineers, it has to be physics. It has to be visual. Okay, you memorize any of this, game over. Forget it. Okay, I'm teaching you in such a sense that when you analyze a structure, you could visualize. Okay, so this is where we identify when it's a moment and when it's a torque. Now, the next one, another formula is due to shearing stress or shearing force. Okay, shearing force. So this structure has shearing force because when you apply a moment, you bound to have a shearing force over here known as V. And you guys have come into this term before. You have shear force diagram and bending moment diagrams. Yes, right? So when Dr. Koshi taught you all beam analysis, there is shear force. You guys construct shear force diagram and you guys construct bending moment diagram. Yes or no? So how does the shear force affect the structure? Okay. So the shear force will induce shearing stress. Okay, I think Dr. Koshi taught this very briefly in class. So you have shear stress is equal to, so our shear stress is in, let's look at our vector now. Okay, so our shear stress is in the y direction. So Vy over Izz Qz divided by thickness. Okay, so what do I mean by that? So Vy, let me define what they are. So Vy is a shear force in y direction. Qz is the first moment of area about the z-axis. Izz, second moment of area about the z-axis. T represent thickness. Okay. Now, shearing stress is one of the most difficult topic. Okay, is one difficult topic. Is it possible that the same force but torque and bending moment happen at the same time? Yes, all can happen at the same time. Everything can happen at the same time. Okay. So this, as I said, this is one of the most difficult topic. I know you guys have done a bit on have you all done shearing stress? Can someone tell me yes or no? Anyone? You guys have seen the formula before? Hello? I got no response. Oh God, that's no good. But anyway, so over here, again, I'm going to draw the same thing. Yeah, I'm going to draw the same thing. Briefly, yes. Okay, briefly. As I said, this is one of the most abstract topic. Okay, so this is your element A again, element B, element C, and element D. Okay, your element A, B, C, or D. So if you look at the shear stress distribution, the shear stress will start. So your B in the Y direction will go like this. Okay, so the shear stress will distribute on the surface. It will go like this. On the surface. And then your end at the center. Okay, so this is your shear flow. What I'm drawing to you is your shear flow. So for this topic, we are going to learn from week 3 up to week 5. Okay, we're going to learn from week 3 up to week 5. And if I'm going to sketch the shear stress distribution, so this is the distance from the neutral axis. Okay, so this is our shear, right? And this is our extreme point. The shear stress will distribute this way. Okay, so over here, this is where your tau max is. Okay, and then the green dot I'm going to draw. I'm still partial color blind over here. The green dot I'm going to draw. This is known as our neutral axis or centroid. Okay. So what we see from here, right? What we see from here, point A and point B and point C have zero shearing stress due to the shear force. Okay. So point A and point C, right? Point A and point C. Point A and point C is 0 down here. Right? And then point B and point D, right? Point B and point D, okay, point B and point D has the maximum shearing stress. So this will you will have By over Izz Qz divided by T. Okay, and then over here you also have By over Izz Qz divided by T. Okay. Now, at this moment of time, you have the full stress analysis. This is what I call analysis. It's not just putting in the formula now. Okay, we now actually have the analysis done, and then from here, okay, we're going to see where and how the structure is going to fail. Okay, and then from here we can relate to the material properties. Can I scroll down, please? Sorry. Okay. Now, one thing that is interesting in this, I'll be done in less than 1 minute. Okay. I want you to look at the distribution of the normal stress and shearing stress. Okay. I will copy this. Okay, and I'll paste down here. Okay. So what you see is a diagram. So the one on over here is a shear stress distribution. Over here is the normal stress distribution. What is something that you see is intriguing? Can anyone see anything? What can you see that's interesting over here about the normal stress and shearing stress distribution? Anyone? What happened at the neutral axis? Anyone?
The max occurs at the minimum. Like vice versa.
You got it over there. Okay. In the shearing stress, the maximum is at the centroid. On the bending moment, the maximum is away from the centroid. Okay. Before I stop, when we talk about shear flow, is that the deformation or just stress? It's just how the shear stress is flowing. Nothing to do with deformation yet. Normal stress is the deviation of shearing stress. Ay. Tony, we need to go more detail into that later. Okay, so for now, I'm going to stop. Have a good day today. I cannot wait to see you at on Friday. Okay, so I'm going to stop lecture here. I'll still be here. If anyone have a question, I'm here to answer your question. Okay, go for your next class.